tackle for you here. So I'm going to try to do these kind of in some semblance of order, and I thought maybe we could work on most of the trig things first, and then we'll get to some of those sig figs pretty soon. So I saw this table for you here, and I thought maybe the best way to explain this to you would be that you can read the table sort of forwards and backwards, because you have sort of opposite angles and opposite functions here. So for example, I think the first way to look at that, it would be kind of ignoring all of this stuff at the bottom here, and likewise ignoring the column here, like this. Then this table reads pretty much exactly like a spreadsheet, like an Excel sheet. So like for example, if you had to find the sine of 36 degrees and 30 minutes. Alright, so let's say we wanted to do the sine of 36 degrees 30 minutes. Then you would come here and see here's 36, here's 30 minutes. So 36 degrees 30 minutes, and then the sine is right here. That would be this value. See what I mean? So you just read it like a table, right? If I wanted the cosine of 36 degrees 30 minutes, it would be the next one over, right here. The tangent, the cotangent, and so on. Honestly, this is really dated because, I mean, most of the time you would never have something like this. Most of the time you would just use your calculator. No reason whatsoever to do this. But just in case, I guess, you might have to do it. This is how you would do it. On the other hand, these tables also work backwards of each other as well. For example, like the sine of 36 degrees, let's focus on just a simple one and look at 36 degrees for a minute. Well, okay, the sine of 36 degrees, 0.578, it's also the same thing as the cosine of its opposite angle. So if we look at the table the other way and look at it like this, okay, then this is from 53 to 54 degrees. They're the opposite angles, the ones that are complementary to the other ones, right? Because you're talking about like two angles that make 90 degrees. So like if we looked at 36 and 54, they're complementary angles. They make 90 with each other. So take the 36 and the 54, put it together, you get 90. As it turns out that if you do the sine of 36, it would be 0.578. But likewise, the cosine, see we're reading the bottom table? The bottom table tells you the cosine, sine, cotangent of this angle. So 54 and cosine is the same value as sine of 36, right? They work opposite of each other. So if you're reading a degree from 36 to 37 off of this, you would use the left column and the top table, right? If you were reading an angle from 53 to 54 off of this, you would use the right column and the bottom table. You see? So it's just about reading a spreadsheet from there. But the lesson, I guess, is that you learn that the sine and cosine and everything that is opposite of each other, cotangent and tangent, tangent, cotangent, you see, they work opposite of each other. So, like, you could tell that, like, you know, everything about this one is exactly opposite of everything about this one. That's the lesson behind it. But really, it's just as simple as reading a spreadsheet. Okay, we'll toss that aside. Go to another one. All right, these ones say to do these to each of the following. First off, let's say the first part of this, I don't know what parts of these you were having trouble with or not, so I'll just kind of do a couple out of each. When it says to use your calculator to find a value of theta, in other words, find an angle, in an interval between 0 and 90 that satisfies each of the following. Okay, well, you're going to need a scientific calculator to do this. All I have with me right now is this kind of old crappy school calculator, but it will do the job. When you're trying to figure out an angle, what you want to do is the inverse of the function in front of it. So for example, like tangent theta equals this. To get rid of a tangent, you want to use the inverse tangent function of each of these things. And what happens is the tangent and inverse tangent cancel, and you get theta equals some value. So if you just have that value, 1.473, and then you would hit, on this calculator, it's kind of hard to see, but maybe you can see where the tangent button is. Right here. See how the tangent button and then right above it there's an inverse tangent button? So I would want to hit second and hit inverse tangent, and I get the degree measure for that angle, 55.8279 whatever. And it says to do this here. Now what I would say is this value is 4 significant digits. We'll get to that in a little bit, I guess. But so our answer needs to be 4 significant digits. So I can do 55.83 when I round that. So I mean, this is just calculator work for this. It's just taking things in reverse to get it out of here. Like secant theta, right? There's an inverse of the secant function as well. Unfortunately, it looks like this old calculator doesn't really have it, but I bet if you have a graphing calculator, it'll do that for you. Also, the secant is like, I think it is like 1 over the tangent or something. I don't remember offhand, but there is a formula for how to do a secant too. If your calculator doesn't do that off the top of my head, I don't remember. I apologize. With the cosine, though, again, this would be inverse cosine. In other words, to find an angle, you just use the inverse function of whatever you're dealing with. So this one would be 0.81, sorry, 0.8616, and I would hit inverse cosine, and it comes out to 30.50 degrees. See how they're all within 0 to 90? Okay, so then looking at the next set down, it says something about do each one of these to 5 decimal places. Again, this is just straight calculator work. So like for number 66, I would say that is, to type that in, you would type 38.1219 and hit the cosine button, and you get this. It's hard to see with the glare. You get 0.7866699 and so on. So it's set to 5 decimal places, so 0.78669 or 6, I think you would do 670 like that, and that would be your answer. If it comes to one of these where you have degrees and minutes and seconds like this, you can turn it into a decimal if you want, but some calculators actually allow you to enter it just like that. So if you have a graphing calculator that you can enter it just like this, I can't tell you the exact key functions off the top of my head, but if you Google how to enter degrees, minutes, seconds onto a TI-82, or if your calculator is a TI-83 plus, something like that, or if you have an even more modern one, just Google how to type degrees, minutes, seconds on a calculator and then hit the cosine button and you can do it. If you want to do it the old-fashioned way and turn it into a decimal, you would divide this number by 60. This is going to be kind of weird. I'll show you how to do this on the side here. Let's do one turning it into a decimal. Let me get a little space here. So if we wanted to turn negative 29 degrees, 3 minutes and 5 seconds into a decimal that we could just use in the calculator, the first thing you do is set aside the whole number degrees. Okay, then you're looking at 3 minutes and 5 seconds. Take the 3 minutes and divide it by 60. So you're going to get a decimal. 3 divided by 60. Check that, sorry. 3 times 60. You know what? I gotta look that up, Liz. I forget. Sorry, give me 1 second. I apologize. Here, I'll show you exactly how I would find this out. I'm thinking you divide that by 60. That makes sense. Yep. Alright. We're not even going to have to look it up. We can do this without looking it up. That's dumb. I should know better than that. Okay, so if you have 3 minutes and you want to turn it into a decimal, you would take 3 and divide it by 60. If you do that, you should get 0.05. So right now what you have is negative 29.05. But then you got to take the 5 seconds part and divide it by 3,600. And that is 0.001389. Round it off a little bit. And then you just add all of these things together. So it would be negative 29.051389. And that would be your decimal. So that's like your degrees in decimal format. Or another way to write it would be 29 degrees, 3 minutes, 5 seconds. So if we go back to this problem, right, and you wanted to do the cosine of that, then all you would do is type cosine of that decimal in your calculator and you get some value for it, whatever it is. That's up to you if you want to do it that way, but like I said, a lot of calculators will allow you to type cosine and enter this in just like that. But if you have to turn it into a decimal, then the way to turn it into a decimal is to divide this number by divide this number by 60 and divide this number by 3,600 and add all the decimals together. Also down here, when it looks like these are again a lot of calculator work, what I did for you here was I took the calculator. If you have a TI 83 Plus or anything like that, you could type this exactly how it's written on here and you'll see that it comes out to -1, I believe. So I mean, like literally if you just type it exactly like that, it'll work out like that. If you have to do these, and again you have to convert them if you have to, right, take the 14 minutes and divide it by 60. So it would be 14 divided by 60 and it would be 0.2333. So this is really the sine of 28.2333 degrees times the cosine of 46 divided by 60, which is kind of what I thought it was going to be, 61.76666, like that. And then you can add it to the other one. You're going to find out that that one works out to an integer also. The point is that to do these, I mean, basically it's calculator work. He even tells you use your calculator to find the following. If you type them straight into the calculator, you'll get answers that come out to just exact numbers. That's what an integer is. An integer is just a regular number, either positive or negative. Okay. Okay, I'm sorry, I can't tell what the directions are for these. I don't know exactly what you were supposed to do with it, so I don't know if this was an issue for you, or if again if it were these that you're having trouble with. But once again, if you have to type this into a calculator, because it says to use a calculator to find the value, again, just type the trig function, and then to do this, if you want a decimal equivalent of it, just divide the minutes part by 60. And if you happen to have seconds, divide the seconds by 3,600, add them all together. In this case, you'd be typing cotangent of 41.3333, so on, and get a degree and get an answer for it. So if you have to, convert it. If you can just type it into your calculator as the degrees and minutes, do that instead. It's even faster. But that's up to you. All right, so then I saw this part about coterminal. Coterminal is such a simple thing. It's really kind of a silly idea. But I think the best way to explain it to you is if I just show you a quick, simple graph. If we do this, I think this could be like a 45-degree angle, right? And so we normally read it from here, like the starting point, up to here, and we would say 45 degrees. But do you understand the idea that if I also did the same kind of angle and I went this way, passing that all the way around and back again up to there, that I could land at the same spot. In other words, it would represent the same angle or the same location away from the starting point. So if you think about it as the start and the end, then I could get there by going 45 degrees, or I could get there by going all the way around 360 and then another 45, which would be a 405 degree angle. In other words, a 405 degree angle and a 45 degree angle are effectively the exact same thing. It's called coterminal. That's what that means. So the best way to figure out what the coterminal angle is to take your angle and you do what's called plus or minus 360 to find it. So like for example, if your angle has to fall between 0 and 360 degrees, then in this case, if I took 708 and added 360, I'm going to be well over 1,000. That doesn't make any sense. But if I subtract 360, I would get 708 minus 360, 348 degrees. So in this case, a 348 degree angle is the exact same thing as a 708 degree angle, because all you're doing is adding 360 or subtracting in this case. In case of this one, again, I would probably subtract 360. Okay, well, so 483 minus 360, 123 degrees. See how easy this is, right? Okay, in this one, if I subtracted 360, I would be even more negative. That doesn't do me any good because it has to be between 0 and 360. So for this one, I would add 360. So you have to do negative 321 plus 360, and you get 39 degrees, and it would still be 50 minutes. Because see, when you're adding whole degrees like that, the minutes part doesn't even matter. It's just the whole digit degree, because you're just saying an exact answer of 360, either adding it or subtracting it. So every one of these, the only difficulty is whether you're going to add it or subtract the 360. If you really have a hard time deciding, just add it first, and if it's a number bigger than what your range is allowed to be, then you can't do that one. Do the other one. It always works, either by adding or subtracting. And again, looking down here, Liz, I'm sorry, I don't know what the directions were, so I don't know what I can tell you about these ones, because I don't know exactly what it was asking you to do. So if it's the same thing, if it's the coterminal angle, just add or subtract 360 over and over again. All right, let's get into the meat of this trig stuff, which is definitely how to do these identities. Okay, so it took me a little while to figure out that basically what you were trying to do here is prove whether these things are true or not, and then of course to do that algebraically. So I'm sorry I didn't get it totally down there, but we can work it out now. It won't take us very long. So here we go. It looks to me like this is the triangle that you would be using to work on. I don't know what the name of this triangle is offhand, but it's basically a generically labeled triangle with 3 angles, or one of them a right angle. So we have C, which is kind of traditionally the right angle, and then opposite of those angles are their lowercase letters referring to their sides. So what we do is we look at the 2 things, or 3 things that we'll need. We need the picture of the triangle, I guess, for reference, but then we need to know what the Pythagorean theorem is. That's something that is fundamental and guaranteed to be true. That if you take the 2 short sides, square them, and add it together, it will be equal to the longest side squared. You know, basic geometry. And then the other ones we would need are the trig functions, the basic ones. Sine, which is opposite over hypotenuse. Cosine, which is adjacent over hypotenuse. And tangent, which is opposite over adjacent. Sometimes we call this SOHCAHTOA. I don't know if you've ever heard of that or not. Hopefully you have. In trig, everybody knows that one. But you know, for reference for our problems here, we'll use A, B, and C, but we'll follow this pattern to it. Okay? So let's get started. All right, number 1, it says the sine of A equals the sine of B. Well, immediately to me, that sounds silly. Because I would think, how could the sine of one thing be exactly the same as the sine of another? That doesn't make any sense at all. It's like saying 1 equals 2. It can't possibly be. But they want to show y, so let's take a look at y. Okay, if we're looking at our triangle, right, maybe you should keep this thing on the side like this for a little bit. Okay, so the sine of A, so here's angle A, right? The sine of it would be opposite over the hypotenuse. So the opposite side of capital A is A, right? And then the hypotenuse is always C. So this is A over C. Okay, so then the sine of B would be opposite of B over C, B over C. Okay, it's mathematically impossible for A over C to equal B over C unless they were the exact same side. So if this was a 45, 45, 90 triangle, then it would be okay. But other than that, it's not. So this is no good, right? Not true. Maybe you could get bonus points if you say except for a 45, 45, 90 triangle. But see, then again, what you're really saying is that the sine of a 45 equals the sine of a 45. So it's not really sine A and sine B anyway, it's sine A and sine A. You see what I'm saying? So it's one of those things where, like, in general, this identity is not an identity. There is no such thing. So this is definitely not true. Okay, this one, again, it seems kind of weird, right? Tangent of A times the tangent of B. Okay, well, A's tangent would be opposite over adjacent for angle A would be A over B, and then the tangent of B would be B over A, which equals 1. Okay, well, we would say A crosses out or cancels, and B cancels. But when you have things that cancel, they don't disappear, they equal 1. A divided by A is 1, and B divided by B is 1. We get 1 equals 1. This is true. Kind of a crazy one. Simple, but true. See how we're just using the basic letters to prove these things? Alright, so then we get one that's a little bit ugly. Right? Let's see what we can do with this. Okay, so we have 1 over the cosine squared of A minus 1 equals tangent squared of A. Wow, talk about a jump in difficulty. Okay, so tangent of A is A over B. But we need to square it because it's the square of tangent A. Alright, over here we have cosine of A. Cosine of A is B over C. But again, it's squared. So we have 1 over that thing squared, and then minus 1. So it seems like a nightmare to me, but let's see if we can work it out. Okay. So let's start simplifying. So over here it would be 1 over B squared over C squared. So we have 1 over a fraction, which is a mess. And then here, A squared over B squared, when you square them both. Okay. When you have 1 over a fraction, ultimately what really happens is you just flip that fraction over. It's called reciprocating. So it's really C squared over B squared minus 1 equals A squared over B squared. So you're like, well, how is that possibly equal? Okay, here's the catch. This 1, we can't really add or subtract it to this fraction unless it's a common denominator. So you have to think to yourself, if I need this 1 to somehow be something over B squared, right? Like, to be able to add it, it's got to be over B squared. So the question is what over B squared is still equal to 1? The answer is B squared. So we're replacing this 1 with this. And it's still equal to 1, you see? Now we look at this. I'm going to come over here and I say, well, that still looks like a giant mess, but I think we're going to make it clean up really quickly. Because they're all over B squared, I can take the entire thing and multiply it all by B squared. And what happens is every B squared along the bottom and that one would cancel themselves out, and I'm left with C squared minus B squared equals A squared. And I think, well, how does that help me prove they're equal? Well, if I do one more thing, if I add b squared to both sides, I get c squared equals a squared plus b squared, which is something that I know is true. That's the Pythagorean theorem. So gosh, I mean, if you were trying to prove this thing, that is a great way to do it. That's algebra practice galore. But this one is true. See? So you're trying to do that same kind of thing every time. Alright, so I was looking at number 4, and I'm trying to think of a way to do this algebraically, but I think that the simplest way to do this would be to try to disprove it. Because a trig identity is true for everything, unless you can disprove it, then it doesn't matter, it's not an identity. You understand what I mean by that? Like, the thought is that something to be true, it has to always be true. It can't be sometimes true, right? Just because you find one way that maybe it works, it doesn't mean that it works all the time. But on the other hand, if you can find a way where it doesn't work, then you've proven that it's not an identity. So I would say that sometimes it might actually be a little bit easier to prove this in some way that shows that it doesn't work out. So I'm going to use a real classic example from trig. I'm going to use a 30, 60, 90 triangle. And 30, 60, 90 triangles have a pattern to them. Again, we'll call this A, B, and C. And they have a pattern. The pattern is that if the side opposite of 30 is 1, the hypotenuse will be 2, and the side opposite of 60 will be square root of 3. So here's what I'm going to do. I'm going to say the sine of A. Sine of A would be opposite over hypotenuse, 1 over 2. And the sine of B would be opposite over hypotenuse, square root of 3 over 2. The sine of the two together, A plus B, which is 90, that's an identity, right? So this is sine, sorry, I should have told you this. This is sine of 30 plus sine of 60. And they're saying it's equal to the sine of 30 plus 60, which is essentially the sine of 90. The sine of 90 is equal to 1 by rule. So if we add 1/2 plus the square root of 3 over 2, what we get is 1 plus the square root of 3 over 2. And as it turns out, 1 plus the square root of 3 over 2 is not equal to 1. So this is not true. You could do it on a calculator if you really wanted to. But let's just, to prove a point, square root of 3 is already 1.73, right? Plus another 1 is 2.73. And if I divide it by 2, I get 1.366, which is definitely not equal to 1. So it doesn't work for even one of the most fundamental trig triangles, a 30, 60, 90 triangle. So number 4 is definitely not an identity. Okay, my favorite one out of all of these that I saw, this one. Okay, I don't know, this was another number 4, I guess. When I look at these, I truly hate, excuse me, to do stuff with fractions like this. So I try to multiply them away. So there might be another way to do this, but this is the way I would approach it. I would look at this and say, wow, it would sure be nice to get rid of this cosine of A. So what I would do is multiply both sides of the equation by the cosine of A. And that would cancel these out and leave me with 1 plus the sine of A equals, okay, I got 2 cosines now, so it's cosine squared of A all over 1 minus the sine of A. But again, I don't really like that 1 minus the sine of A there either, so I'm going to multiply both sides by 1 minus the sine of A. And that will cancel this. So I get cosine squared A here. And over here, this is like FOIL, or better yet, just multiplying two binomials. So when you do this, you have to take the 1 times both of these things. So 1 times 1, 1 times the sine of a, which is still the sine of a. Then you have to take negative sine of a times 1, which is still negative sine of a. See what happens there? They're going to cancel out. And then I take negative sine of a times sine of a, so I get negative sine squared a. Alright, from there, I let the sines cancel out and I get 1 minus the sine squared of a equals the cosine squared of a. And now I finally go back to the sides of the triangle here and work these out. So I would say that 1 minus, okay, sine squared a. Well, sine of a is a over c, but to square it, it's a squared over c squared. And then the cosine of a is b over c, but to square it again would be b squared over c squared. So you can see again that we're still in that position where we have this 1 that is not in the same pattern as the others. So just like we did with that other problem, instead of this being a 1 written like this, I'm going to write it over c squared, but to do that I got to make it c squared over c squared minus a squared over c squared equals b squared over c squared. But I think maybe you can see where this is going, just like the other one. Now that I have all these c squareds here, I can multiply the whole thing by c squared and allow it to cancel all of that stuff on the bottom, and I'm left with c squared minus a squared equals b squared. And if I do the last step to add a squared to both sides, I'm back to the Pythagorean theorem again, which I know is true, which means that our original thing was true. It's kind of funny because some of these seem really long, like that one, which is like a great exercise in algebra, but on the other hand, then you get to number 5 and it seems like a pretty easy one. The tangent of a would be a over b, and the cosine of a would be b over c, and the sine of a is a over c. You can see that the b's are canceled and you get a over c equals a over c. That one's true again. Okay, this one says cosine of b. Alright, that's a over c equals 1 over the sine of b. Sine of b is b over c. Okay, so if you take that and reciprocate it, a over c equals c over b. Well, that's not true. Okay, I like number 7 too, but again, number 7 I would use a little bit of a different approach to this. I would say that I know that the 3 angles of a triangle, because see, we're talking about the degrees here and comparing angle A and angle B. What I know from any triangle, is that A plus B plus C, the 3 angles, have to equal 180. If you allow the idea that C is always the 90-degree angle, then what I have is A plus B plus 90 equals 180. So if I take this and I subtract the 90 away, I get A plus B equals 90. And so if I want to solve this for A, then I would subtract B from both sides, and that would give me A equals 90 minus B. So if you look at our problem for a second, right? What this says, you can read it as A equals 90 minus B, but it also means that anywhere there's an A, you could replace it with the whole expression 90 minus B. So in this case, you would take out the A and say 90 minus B equals tangent of 90 minus B. And so you've proven that A is guaranteed to be 90 minus B. This one is also true. So I go and I look at the next set again. All right, I'm on to cosine B equals sine B. Again, I would say, how could that possibly be the case? How could cosine B equal sine B? But just to prove a point, cosine B is A over C, sine B is B over C. There's no way they're the same unless, of course, you had a 45-degree angle for each, like a 45, 45, 90. So this is not true for all but one pair of type of angles. Okay, we have tangent B equals 1 over tangent A. Tangent B is B over A equals 1 over tangent A is A over B. This one, again, if you do this, that's just a reciprocal. When you reciprocate, they're exactly the same. This one is true. If we look at cosine of B equals 1 over sine of B, cosine of B is A over C. 1 over the sine of B is B over C. So what we get is A over C equals C over B. And again, that's not true. I think that was the same as another one we did. Okay, number 8. My second favorite one compared to that other number 4. Okay, here goes number 8. First thing I would do is actually multiply these things together. This is cosine squared B tangent squared B plus cosine squared B. It's supposed to equal 1. It's kind of like too complex to think that it could be true, but at the same time you kind of figure it probably is true because, you know, some quirky stupid trig thing. But okay, cosine of B is A over C, but we know that's really A squared over C squared times tangent squared of B is B over A, but it's B squared over C squared. And those are multiplied together. Let me make sure I did that right. Yeah, I did. Okay. Plus cosine squared of B, which is the same thing we had earlier, A squared over C squared. So we have to multiply these things together and then try to add them. We'll see what happens. Okay, if I multiply these, oh, you know what? I'm sorry. I made a mistake in this one. I didn't think that was right. Let me go back to this. Sorry, Liz. Tangent squared B is B squared over A squared. Sorry about that. That makes a huge difference. Okay? And this all equals 1. The reason why that makes a huge difference is the A squareds cancel. And so what I'm left with is B squared over C squared plus A squared over C squared equals 1. But again, to compare these things, since these are all over C squareds, I'm going to write this 1 as C squared over C squared. Starting to see a pattern to those kind of solutions. And we take this, multiply the whole thing by C squared to cancel them all off, except for the one on the top, right? And we have B squared plus A squared equals C squared. That's a, if you flip them around, that is the Pythagorean theorem again, which means that this is true. So that was a whole bunch of trig identities proven there just for fun. Alright, let's look at this one. It came from Snell's Law. I wrote all over your first paper here that I printed out, but the Snell's Law one is this stuff. Right, where you have, what this is a light beam coming from one substance, like say air, and contacting water. When it hits the water, it bends and actually slows down a little bit. This process is called refraction. This is actually a physics problem, but I guess they wanted to give you some context behind your trig. So there is a formula for Snell's Law. It looks like this. And so we're just going to apply that basic proportion to the two kinds of problems you had. The first kind of problem asks you to find the second velocity. So, I mean, basically we're just substituting some numbers in. So this would be sine of 46 degrees over sine of 31 degrees equals V1, which is 3 times 10 to the 8th, over V2, which we don't know. But this goes back to algebra days, Liz. This is cross multiplying. You're going to take V2 times this and that times that. So what you really have is V2 times the sine of 46 degrees equals 3 times 10 to the 8th times the sine of 31 degrees. So if you really want what V2 is, then you would divide both sides by the sine of 46 degrees. And you get your second velocity. So I mean, this is just from this point on is calculator work. I would take sine of 31 times 3 times 10 to the 8th, and then I would divide by the sine of 46. And it looks like we should get a big number, of course, because it's something times 10 to the 8th. I'm going to make sure I did it correctly, just to make sure. By the way, if you like to use decimals here instead, you could have this as 3 times 10 to the 8th times 0.515 all over 0.719. And so if you work this out, you're going to get a second velocity that is 2.1488, we have a long number for now, times 10 to the 8th. And I guess since you are using significant digits here, 3 times 10 to the 8th, to me that's an exact value, but at the same time I would trust that this is one significant digit. If you made this one significant digit, it would be 2 times 10 to the 8th. But, you know, I don't know if that's what they want or not here. But if it is, you know, make sure you use your significant digits the way you're supposed to. But I would do 2.14 times 10 to the 8th as the second value. But again, they may require to use significant figures, which would knock that all the way down to 2 times 10 to the 8th. If we do this one, this time we're looking for the second angle. It's going to require us to do a similar calculation. It's going to be slightly different. We'll do sine of 40 degrees over the sine of our angle equals 3 times 10 to the 8th over 1.5 times 10 to the 8th. Now see, you can make this a lot easier on yourself because you can cancel the times 10 to the 8th parts. And really this is 3 divided by 1.5, which is just 2. So I have sine of 40 degrees over sine of theta 2 equals 2. I multiply both sides by the sine of theta 2 so that those can cancel out, and I get sine of 40 degrees equals 2 sine of theta 2. So I divide it all by 2 to cancel that number out, and I type the sine of 40 divided by 2. I'm going to get 0.3214 equals sine theta 2. And from there I need to do an inverse trig function. I'm going to take the inverse sine of that and the inverse sine of this number, this way these will cancel and I'll be left with just theta, and I get 18.75 degrees, which again, I guess for significant figures purpose you might need to round that to 19 degrees. Either way. Alright, Liz, that is the trig stuff. I'm going to stop the video there and save it, and then I'll make you one for the significant digit stuff. Actually, check that. Let's just do it all at once. That way we don't have to take any more time pausing this thing. Alright, so we're going to look at significant figures then. Okay, so I see a whole bunch of significant digit problems here, and I was trying to figure out a way that I could explain it to you that would make it kind of like nice and complete and concise. So I came up with some basic rules for significant figures, if I can find it. Give me 1 second. There we go. So here would be my rules for significant figures. Okay, basically start out with something real simple. Rule number 1, every regular number other than 0 is always a significant digit. So if you're counting, in the case of 21.8, there are 3 regular numbers there, significant digits 3. In the case of number 16, 37, significant digits 2. Right? Regular numbers are always significant. The second one's also fairly easy. Zeros between other significant digits are significant. So if I look at number 17, I know that the 4, 2, and the 8 are significant figures, which makes me think 3, except that that 0 is between 2 other significant digits. So this one is 4, because that 0 is a significant digit. The last one is all zeros to the right of the decimal point are significant as long as there's at least one significant digit to the left of the decimal point. Wow, that's a mouthful. Okay, so how do I determine this? So I start with all zeros to the right of a decimal point. Okay, like look at number 24. Right? There's the decimal point, there's zeros to the right of it. Okay, they're only significant as long as there's at least one significant digit to the left of the decimal point. See, here's one to the left. So all of these are significant then, 5. But here's an example of one that doesn't work that way. How about this, 0.0089? Okay, the thought on that is how many significant figures do you have? Well, again, right, to the right of the decimal point I see 3 zeros. My first thought would be, well, okay, those zeros are significant because they're to the right of the decimal point, except that there has to be at least one significant digit to the left of the decimal point, and there isn't any here. So in the case of this number, these 3 zeros are not significant digits, only the 2 on the end. So the answer to this one would be 2 significant digits. So you can go through all of these and try to figure that out, right? I put answers down here for some of them. 3.0 times 10 to the 7th. The zeros after the decimal point are on the right, so it's questionable, except that there is a number to the left. So yes, it is 2 significant digits. This one's easy, 3. How about 20,000? Okay, here's where sometimes people run into problems, right? 20,000, all of these zeros, they're not significant because none of those apply to this rule, right? All zeros between other significant digits. Well, here's 1, but where's the one on the other side that is a significant digit? There isn't. And how about number 3? All zeros to the right of a decimal point. Well, these are not to the right of the decimal point. The decimal point would be here. They're to the left. So these are not significant digits. Only the 2. So this is 1 significant digit. I think the best way to do these kind of problems is to write them in scientific notation. Scientific notation really helps you figure out how many significant digits there are. My guess is that's the best possible way to write it. Okay, so I like some of these word problems. I thought we'd look at those. As you can see, I wrote some of my answers up here. I'm gonna take this off and write them on the back. So the first question about Mount Everest or whatever said that they gave a measurement of 29,000 feet. Okay. And then it said what would happen if it was 29,002 feet. Okay, basically, when you look at these things, right, if you were to write it in scientific notation, this decimal point gets moved back to here. This is 2.9 times 10, and then there would be, what, 1, 2, 3, 4, times 10 to the 4th feet. Okay, this one is the same thing except it's 2.9002 times 10 to the 4th feet. Okay. Let's look at this from this example then. They're talking about what is an acceptable range of values. Okay, the thought is that this last number, you would say, well, what would it take to round up or round down to get 2.9? So let's set this on the side for a second. If you were thinking about all the numbers that would round down to 2.9, right, with one thing, all I do is take this last number and I go down by a half and up by a half. So from 2.85, because I took this last number and I'm saying, well, go down by 1/2 of an increment off the end, and I'm going to go up another 1/2 of an increment to 2.95. Actually, do you understand that like this number is right in the middle of these? But see, all I did was move it by a half on each side. Right? This is 0.05 below and 0.05 above. Right? So see, the thing is though, if you write it like this, 2.85 times 10 to the 4th to 2.95 times 10 to the 4th, but if you write out those numbers, this is 28,500 to 29,500. See, this is the key, right? Drop it down by a little bit. Now this one, you're going to have a little bit more work to do that, right? It would be 2.9002, but we would split that into 2.900015, because I knock it down in a half, right? And then I go up a half, 2.90025. And so if I were to rewrite that in scientific notation, I would be saying 2.90015 times 10 to the 4th to 2.90025 times 10 to the 4th. If I move it to 4 decimal places, I got 29,001.5 feet to 29,002.5 feet. See, scientific notation, and even better yet, significant digits, is a representation of how precise a measurement can be based on the way the number was written. This is a much more precise measurement than this is. I know that it looks on paper like it's only 2 feet off from each other, and in practical sense it is, but what they're trying to show you is that it's a method of writing to indicate or reflect how precise you were measuring it. If you say 29,000 and that's the best you can do, you have to think about what numbers would round up to 29,000, rounding up to the nearest thousand, right? So anything from 28,500 up to anything from there up to 29,500, all of the numbers in between those would round to 29,000 if you round by the nearest thousand. And that's what this indicates to do, because there's only 2 significant digits, which means that it's relatively unprecise. But see, this one is 5 significant digits. Five significant digits would be a lot more precise of a measurement. And as it turns out, when you write it in scientific notation and you create that range by dropping it by a 0.5 and raising it by a 0.5 on the ends, you can see that this kind of measurement turns out to be a much more exact range than this one is, right? This is 1,000 feet off, on plus or minus 500 we would call it. This one is plus or minus half a foot. So that's a totally more precise measurement than this one is. Okay, how about the other one then, when it was talking about calories in food and it says 472 calories. 472 calories. If I asked you how many significant digits that is, hopefully you would tell me 3. And if you wrote it in scientific notation, it would be 4.72 times 10 to the second. But again, we want a range of values, so we would split 4.72 into 4.715 and 4.725. That's our range, right? So if we rewrite it, 4.715 times 10 to the second up to 4.725 times 10 to the second. That's really 471.5 to 472.5 calories. So again, with 3 significant digits like that, it's a very precise measurement down to just a half a calorie either direction. And what they were saying is do you really think, in your opinion, that the company could give it to that level of accuracy, down to a half a calorie? My thought is maybe yes, but they're saying if you wanted to have a little bit more of a potential range of values where it would still be okay, as if the company didn't lie to you or whatever, right? Somebody could claim, well, this thing has 469 calories in it. You said there were 472, you're way off, or something like that, right? Because look at your acceptable range of values. Okay, but realistically, I think we know that 472 and 469 really isn't that important in this situation, right? Like, what's the difference amongst 3 lousy calories? So, what if you change that and just said 470 calories? So this is precise, 3 significant digits. This is less precise because there's only 2 significant digits. Okay, again, if we change this just a little bit to scientific notation, 4.70 or 4.7 times 10 to the second, well, then we would make it 4.65 times 10 to the second, and go the higher end, 4.75 times 10 to the second. That range is 465 to 475. Now you have a plus or 5 calorie swing. So if somebody said, well, the measurement actually 469, well, okay, based on our representation of 470 as an approximate value, 469 fits within our acceptable range of values. So you see, sometimes it's actually better to have an instrument that is slightly less precise in calculating, because you're actually better off describing it that way. Getting a measurement as precise as this one might actually push you to a degree of precision that is unattainable for what you're working with. So it's just 2 examples of word problems where you show significant digits and their effect. But the key is, when you do a range, I always like to put it in scientific notation, so that I can easily drop that down by 0.5 and raise it up by a half, just to give you a range of values, right? I'm not dropping it like by 0.5, I'm dropping it by a half of this unit and raising it by a half of that unit. So a half of a 10th unit is a 100th unit. You see what I mean? Okay, let's look at some more Sig Fig stuff on here and see if any of the other ones make any sense here. How about this one? So I was looking at this and I was thinking, wow, you know what, it seems like it really makes sense. There's 1 significant digit here and 2 here. So I get that 2 times 65 really is 130, but if you were following the rules using the lowest number of significant digits possible, then there's only 1 here, so the answer should be 1 significant digit. Okay, but the problem with that is that You have to remember that significant digits are measurements, right? Something that you would measure. It's not necessarily a quantity, it's a measurement. So if what you're doing is not a measurement, then significant digits doesn't so much apply, right? Like in the case of measuring the amount of calories, that's a measurement of the amount of calories, right? The measurement of the amount of feet of something, again, significant digits matter. But in the case of this, you either have 2 baskets or you don't, right? Same thing here, 65 apples. You either have 65 apples or you don't. So it's an exact number. So it's okay to use exact numbers in this case. So all of this is like hogwash because you actually have exact numbers. You only use significant digits if what you're dealing with has the potential to not be accurate or exact to that number. And that's the great example of the next one too, right? Circumference is 2 pi r. In this formula, the 2 is an exact number. It's not something that has the potential for a range of values. So that is not reflected in the significant digit thing. Significant digit is only reflected in things that actually have a potential range. Like for example, it's cut off here, Liz, I'm sorry, but if it was just 98 centimeters, right? I don't know if there was something in front of that or not. But 98 centimeters, that is 2 significant digits, and it is a measurement. So if you use this, right, I see that like you work it out with pi or whatever, so it says, and you get this as an answer. Okay, it's not the 2 that matters, right? It's this that matters to 2 significant digits. So you should take this and make it 3.5 times 10 to the second. Right, that's what's wrong with this. Or in other words, 350 square centimeters. See what I mean? So the important part of this is that recognizing that formulas, for example, that have a number in them, that is not a significant digit, right? You could write 2.0 and it could go on forever because the exact value is not subject to significant digits. But anything that we measure, like say 98 centimeters, is subject to significant digits. So you have to be careful what is and what isn't. But like whole value quantities, like the number of apples, right? That's not a measurement. It's just there is this many or there isn't that many, right? So you got to look at those problems and say, you know what, the mistakes are always in people using significant digits when they don't apply. Okay. Oh wait, on that page, these say to change these to 3 significant digits. Well, the only way you can do that is to write it in scientific notation or just write the number without the last significant digit. Like in this case, 3 significant digits would be 12.5. Or, if you wanted to, write it as 1.25 times 10 to the first. If you had to do, as it says, to then do it to 2 significant digits, take this to 2, well then you would round it up to the nearest 2 digits. This is the first 2 digits, so you're going to round it to the nearest one, it would be 13. Or 1.3 times 10 to the first. Can you see how less precise it gets the less number of significant digits you have? That's a great lesson in understanding why you would do it. This one, 3 significant digits would be 921. 2 would be 920. Here, 3 significant digits is 916. 2 would be 920. So you see, if you're using something that's only precise enough to give 2 significant digits, number 28 and number 32 would be the same answer. But they are definitely not exactly the same according to this, but it depends on how many significant digits. Even at 3 significant digits, you can see that they are quite a bit different. But at 2, they're not. They appear to be the same. That reflects a level of how precise an instrument you are measuring with. So I think this was something we kind of already covered, and I think this is as well. So then it's down to these last things with operations. These are not as bad as they look. They look like a giant mess, but they're really not that bad, okay? What you need to look at in the original problem is to decide how many significant digits you have in terms of your final answer. And the way you do this is very, very simple. You can only give it to the minimum number of significant digits you have in the problem. So like if I look at number 54, I'm sorry this is so blurry. When I printed it, I guess it's just about as good as you can do. This says 0.98352 and it's squared. Okay, there are 5 significant digits here. So that means your answer can be written in at most 5 significant digits. So if you just type that on your calculator, if you type 0.98352 and you square it, you get, when you write out the first five significant digits, you get 0.96731, and you round this last one. There's another 1 after it on the calculator, so I would just round it back to that 1, and that's your answer. So let's look at one that has mix of digits. This is 0.425 times, I think that says 89.3 times 746.91. Okay, well, this is 5 significant digits, this one's only 3, and this one's only 3. So the best I can do is 3 significant digits. So I go through and I'm multiplying 0.425 times 89.3 times 746.91, and I get 28347. Here's what I get on the calculator: 28347.10178. That's a whole host of significant digits. Okay, so what I want to do is make sure that I only use 3. So I could write 283 and then a bunch of zeros, but usually you write this as scientific notation like this: 2.83 1 2 1 2 3 4 times 10 to the 4th. So when you're dealing with scientific notation or whatever, when you're dealing with significant digits, just look at the original problem and say to yourself, how many significant digits do I have? What's the lowest number? No matter what. And you'll come out with an answer that'll be in the correct significant digits. The rest of it is just using a calculator to calculate it out. You have to type the stuff in the calculator. If you have a nice graphing calculator, you could probably type the whole thing in there and just make sure you take that final answer and turn it into correct significant digits. Notice that, I don't know if it says it in here or not. Here, never round immediate results. So you're not supposed to round it until the very end. Right? So if you have to do this thing in parts, some of these you might. If you have to do it in parts, then you do the parts and leave them as whole long numbers, but then round the final answer. So like I look at number 60 and I see, I think that says, I can't tell if it says 2000 or 2.00. I'm going to go with 2.00 for now. And this is all divided by 74.83 times 0.0251. So I look through and I'm looking for significant digits. This one has 4. Zeros to the right, as long as there is a number on the left, you're good. So that's 4 significant digits. This one has 4. This one, on the surface, people always say 4, but remember that 0, often called a leading 0, is actually not a significant digit. So this one has 3 significant digits. So I'm going to be limited to 3. But the first thing I do is I calculate out what I have here. I have 2.00, and then on the bottom I do 74.83 times 0.0251, and when I get that answer, it's 1.878233. So I'm not going to round that yet. I'm going to take that answer, 2 divided by that answer, and I get 0.5324415, so on, but I need to stop at 3 significant digits, so it's 0.532, the next number is a 4, so I would round down. That is your correct answer. Right, so it's always about how many significant digits you have in the beginning, but you don't round anything until the very final answer. All of these, even these big problems, are the same concept, right? Scientific notation problems. If you multiply this through, right, how many significant figures did it have? 3. So if you multiply this one out, ultimately what you need to do is write your final answer with 3 significant digits. So 1.66 times 10 to the 4th times 2.93 times 10 to the 3rd, and it comes out to 4863800 on my calculator, which of course is a crappy old one. And I need to write it in scientific notation, but only to 3 significant digits. So really it's 4.86, and I stop, times 10 to the 1, 2, 3, 4, 5, 6, 7. Final answer. So it works the same way as all the other sig fig problems. Just make sure that you decide how many you have in the very beginning, the minimum number you have, and then go from there. But keep in mind that when we're talking about those word problems and stuff like that, like we had in the very beginning of that, right, with Mount Everest and all that, or in the case of the apples one here, right, remember that some parts of those calculations are not subject to significant figures like the measurements are. For example, the 2 here is not something you would worry about its significant figures, but the radius of 98, you would. Alright, Liz, I hope this helped. I saw your prom pictures and stuff. They were great. I love your shoes. Take care, Liz.